Welcome to Unit 5, Part H, and this is the last of a very long lesson on quality control. And what I'm going to be doing in this part is doing little basic statistics, one-on-one, baby statistics. I know some of you may be taking statistics at the same time that you're taking this course. So this is targeted for you, or it may have been a while since you've taken statistics, or you may have forgotten some of the things about statistics, and this could also be a little reminder for you. So what we're going to be studying in this part, and what we're dealing with primarily with statistical process control, is the normal distribution curve. So Walter Shewhart's work in statistical process control has proved to us that when we plot our data in control chart, the variability in the data is guaranteed to be normally distributed. In other words, a normal distribution curve. And this is sometimes referred to as the central limit theorem, which says that all the data is guaranteed to be a normal distribution. So let's talk a little bit about the normal distribution curve. Now what this slide shows is two normal distribution curves. Take a close look at the diagram. We can see one normal distribution curve that is kind of tall and kind of skinny, and I have labeled that distribution number 1. And we see another normal distribution curve, which is a little shorter and a little fatter, and we've labeled that normal distribution curve number 2. Now, what normal distribution curve number 1 and number 2 have in common is that they both have the same mean. So the two primary parameters in the normal distribution curve is the mean and the standard deviation. So the mean is nothing more than the arithmetic average. So for example, if I look at the grades in a particular class, I add up everyone's grade, divide by the number of students who took the exam, and that is the mean grade of that exam. That's all it is. So distribution curve 1 and distribution curve 2 have the same mean. Now, the normal distribution curve is perfectly symmetrical around the mean. It's perfectly symmetrical. So what that means is, of all the data, 50% of the data is going to reside from the mean all the way out to plus infinity. And the other 50% of the data will reside to the left of the mean and all the way out to negative infinity. So it is perfectly symmetrical amount around the mean. The other primary parameter of the normal distribution curve is the standard deviation. The standard deviation. So the standard deviation is a measure of the dispersion of the data. Another way of saying dispersion is how far spread out the data is. So even though normal distribution curve 1 and 2 have the same mean, they do not have the same standard deviation. We can see that distribution curve 2 is wider. The data is more spread out. Therefore, the standard deviation for distribution curve 2 is going to be greater than the standard deviation from distribution curve 1. So once again, The primary things I want you to get out of this slide is that the normal distribution curve is perfectly symmetrical around the mean. 50% of the data falls on one side, 50% of the data falls on the other side of the mean. The standard deviation is a measure of how spread out the data is. The greater the standard deviation, then the greater the dispersion of the data. Now there's another parameter in the normal distribution curve that seems to give students a lot of difficulty for some reason, and that's called the z-value. The z-value. So before we talk about how the z-value fits into the normal distribution curve, I want to give you an analogy of what a z-value is with maybe something that's a little bit more familiar to you. Now remember, this is just an analogy. So we know that in good old Mother Earth, we have an imaginary line that goes right through the center of the Earth, and we call that imaginary line the equator. So if you were on the equator and you look down at the ground, you're not going to see a line that says equator on it. It's an imaginary line that goes through the center of the Earth. And for navigational purposes, we have created something called latitude. We've also created something called longitude, but what I want to do in this slide is to focus in on latitude. So latitude is a reference, is a distance away from a reference point. In this case, the reference point is the equator. So how far away is a particular city or someplace? Its latitude, distance from the equator. And latitude is measured in degrees. Since the Earth has an arc to it, how many degrees of arc is that particular city different from the equator? So at the equator itself, the latitude is 0 degrees. It's sitting right on the equator. So as I move off of the equator, either going north or south, then the latitude will increase in degrees. But again, it is always a measurement with respect to a reference point, and the reference point is the equator. So taking that analogy and carrying it forward to the normal distribution curve, the z-value, which we talk about in the normal distribution curve, is the equivalent to latitude. It is a distance away from a reference point, except the reference point in this case is the mean. It is the mean. So how far away from the mean is a certain percentage of the data? So the z-value at the mean is 0, just as the latitude at the equator is 0. Now we measure z-values in terms of numbers of standard deviations. We measure latitude in degrees, but we measure the z-value in terms of the number of standard deviation. So at one standard deviation away from the mean, z is equal to 1. At 2 standard deviations away from the mean, z equals 2. So let's don't let this z concept throw us into confusion. It's very simple. All it is a distance away from the mean. At the mean, z is equal to 0. So if we had a z-value of 0.5, we're talking about half of a standard deviation away from the mean. Now, you will be asked in a homework problem to determine what the z-value is for a particular percentage of data in the normal distribution curve. So how do you go about determining what z-value would correspond to a percentage of data in the normal distribution curve? So let's take as an example, we would like to know what z-value will represent 90% of the data in a normal distribution curve. In other words, how far away from the mean on both sides represents 90% of the data. Now we know that the normal distribution curve is perfectly symmetrical around the mean. So 90% of the data, we assume that 45% of that half of it, is going to fall between the mean and to the left of mean, and the other half, the other 45%, will fall between the mean and to the right. And the z-value will be the same for both sides. The only thing is, when we measure z-values, we have to distinguish as to whether it is a positive z or a negative z. So for convention purposes, a positive z-value is a distance to the right side of the mean, and a negative z-value is a distance to the left side of the mean. So what I've done in this slide is to kind of give you a little procedure on how to look up in the tables that will be provided to you what the z-value is. So the first step is to take the desired percentage and divide that by 2. And we've done that. So 90% divided by 2 is 45%. The second step is to take that percentage and convert it to a decimal. So 45% as a decimal would be 0.450. That's fairly straightforward. Now, we're going to take the tables that will be provided to you, and there will be rows and columns in the table, and we're going to find the closest value in the table, the closest one to our decimal, 0.450. And once we've done that, then we can read over to the left-hand side, which is the row, and pick up the z-value for that row entry. Read up to the top of the table, and we have another z-value, which is the column z-value. So now we have a row z-value, we have a column z-value, and we're just going to add these two z-values together. And once we've added them together, then that will be the z-value that would represent 90%, or whatever percent is given. So it will be plus z, which would be the right-hand side of the data, and minus z, which will be the left-hand side of the data. So I hope this is clear enough to you to understand some of the basics concepts of the normal distribution curve and also this z-value. So you will have to use this in your homework for this chapter, and you most likely will also see something like this show up on an exam as well. So this will conclude part H of this unit.